Hi, this is Mark, and this is the first video of the series Algebra 1 Simplified. For this video, I'm going to explain where the real numbers come from or what they consist of. It's very important before delving into the coordinate system or development of the coordinate grid. And we're going to start working in one-dimensional space. So with this, this is divided into sections, the blue section and then the red section, and then zero. Essentially, these are the set of integers right here. So what this arrow denotes, if you go, this goes towards positive infinity, and then this arrow, this is called a array. This goes towards negative infinity. So basically, this array extends onward in any direction. But you notice right here, this is a set of countable numbers, positive, negative, and zero. So integers, so this is broken down. What we end up having is if we have a set of elements, so we can represent this circle consisting of a set, and we can define this as the real numbers. Anytime you have a set, a set is just it's a way to depict where to define a boundary. So basically, this is just a boundary of real numbers, meaning like there exists imaginary numbers as well and complex numbers which exist outside of this set. So what ends up what a set represents is it's comprised of individual elements, and individual elements within this set consist of the real numbers. But within each set, there's also subsets. So we can define, for instance, I'm not going to draw this to scale, but essentially the set of integers, we can represent this as integers, resides within the set of real numbers. Integers consist of all the positive, negative, and whole numbers, and include zero. So basically, integers right here, you can define it. So if we put it in a set notation, this would be dot dot dot, and we could have like -3, -2, -1, 0, 1, 2, 3, and then close set. So this is a set notation. And then this dot 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 implies that it's extending towards negative infinity in this direction, and the dot 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 on this side implies it's extending to a positive infinity in that direction. And then we have zero as well, so it's included. So all the elements in here we could have -3, 2, 0 somewhere in here. So they're all going to be within that. All these elements right here, these are the individual elements. So these are the elements. And these elements are within the set. And basically anything outside this boundary does not exist within that set. So we also have the blue section right here, well, not including zero, consists of the natural numbers. And the natural numbers resides within here. So basically, the natural numbers consist of all countable numbers greater than zero. So we can write natural numbers. And if we do in set notation, we just start with 1, 2, 3, dot, 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 so it continues towards infinity. So basically, again, it goes towards infinity. But in this case, it starts with 0, so this is just all countable numbers, right? Whole numbers greater than 0. So in this case, we denote another thing that we can consider. So this is basically within this set. So this is a subset of the set of integers. So how we represent this is if we define if I equals integers, n equals natural numbers, we know that n is a subset of I. Now, subset is analogous. So subset is like analogous to less than or equal to sign. Notice they're very similar. This implies equal elements, equal number of elements. This implies equal quantity. So these are just elements. They could be colors. They could be any element. It abstract any abstraction. This is just a number, a numerical value quantity. So you could just say, if we normally say, okay, we know 4 is less than 5. But it's also true that 4 is less than equal to 5. And this is because this denotes less than or equal to. So anytime you use an or, this is a true statement. If it follows either case is true, the whole thing is true. So it's either or case. So essentially these are both true because 4 is less than 5. 4 is less than 5. It's not equal, but the less than holds true. So therefore it's still true. So in this case, we really know that n is a subset. It's proper just because you know it has less elements. Doesn't include 0, doesn't include the negative number. And then you notice on this number line, we also have space in between these elements. So I could cut this in half, for instance. I could cut it in fourth. You cut a piece of a pie. You have a whole number, like a whole pie, and you cut it into fractions. So if you divide a pie any such way, we could divide a pie in half, and then we could divide it in fourth and so forth, and then divide it in eighths, and then we can keep dividing. And the key here is, although we can continue to divide by whole numbers, whole sections, because this is I'm dividing in 4. It's a whole number, so it's like the reverse of this number line. So what I mean by that is, like, essentially we're going to get in. We're going to talk about rational numbers, which is essentially any fractional or number with a fractional unit. So rational numbers here, I'm going to show, is an even larger set. So basically this is going to be rational numbers, and I'll explain it next. So let's get into rational numbers here. So this is a rational. So this right here is rational numbers. And then we can denote this as a set of P over Q. So this is like a fraction, such that, so this also means such that. It's important to know mathematical notation. So any line that goes vertically like this denotes such that, or P over Q based on the condition that. It could also be that. So P and Q are integers. So basically, so what this means is, like, okay, P could be 1. Let's just say P equals 1, and Q is any integer. Let's just say greater than 0. So it'd be a natural number. So we can do 1 over 1. Well, this equals 1, which is, we know is a natural number or integer. And then we have 1/2, which is a rational number. So basically we can't simplify it. So, then you get to 1/3 and you keep going, 1/4, 1/5. This is like cutting a pie into thirds, cutting a pie into fourths. You cut it into smaller and smaller fragments. So this will continue. But then we also have what we can constrain. We can have, next case we could have p equals 2, and we continue this case. So then we have 2/1. Well, this equals 2, and that's again integer or natural number, and then we have 2/2. Oh, that's 1, and then this is also integer, and then we have 2/3, and then for all cases now, notice how now we're considering now 3. Now, if q is greater than 3 or greater than 2, p over q, because we know p is 2, is a rational number. Because it continues to be divided into smaller and smaller fragments. Eventually we're going to go into like, 2/4, which again, it goes back to 1/2. And then we're back here. We're back, and then we iterate again, and so forth. If we go to p equals 3, we have 3/1. Well, this is integer. We have 3/2. Well, this is again, this is 1.5, so that's a rational number. And then we have 3/3. Well, we know that this is a integer. Okay. And then we also have, so this is an odd component right here, and you notice that it's oscillating, and then we have 3/4, which is again, rational number. But then notice, 4 and then 3/5, and so if you continue, it's just going to continue to be, we won't be able to simplify it. Once you get past the p as an integer, it remains a rational number, and then we break it into smaller. But notice how, like, if we go 3/5 and then 3/6, well, once we get to 6, 2 times 3, we're reverting back to here. And so they're going to go like in a cycle. These continue back in a cycle. And so basically they're going to be the intermediate. They're going to be within this space. However, there's also going to be cases where there's going to be numbers that cannot be simplified in fractional form. So basically, even though we keep dividing like the pie, there's always going to be some space. No matter how, small or how many divisions we create, there's always going to be more divisions, and we continue, and basically there's going to be some space in between. There's always going to be some area. So what that area comprises of is this outside is irrational numbers. So this is the remainder of the real number set. So this is anything outside of the rational numbers becomes irrational. So right here, if you have like 0 to 1, for instance, you start with dividing by half, and 0 to 1. You could divide by, or this would be division by 3. And 0 to 1. You could also divide by 4. So you notice this becomes half again. So we're back into right here. But you also notice it's like a triangle. You start with one node, and you have 2 nodes, kind of like Pascal's triangle. then you have 3 nodes, and you continue in this direction, and it keeps expanding infinitely. But no matter, like, the divisions, we're going to get back to the, whether it's whole numbers or back here, it's going to revert back and cycle back and, keep cycling back. But ultimately, we have some individual space here, and we're eventually going to hit another. We're going to break this in half. We're going to break that in half. And then it's going to get smaller space. But you're going to hit these, there's going to be these points that are still going to be in between that you're never going to hit. And this is where you get into irrational numbers. So if we're going to define irrational, so basically, so this is like equal to, so this is like a square root of x, and we have such that we know that x is not a square for instance, like x is not equal to y squared. So x is not a square, and yeah, essentially that's what it holds true. So basically, for instance, suppose x equals y squared. So this would be a case like x equals, let's say, 5 squared. So this is like y equals 5. This is a case, y equals 5. Okay. So notice now we take this. We're taking square roots of 5 squared. And this is equal to square roots of 5 times 5. And basically, or we could represent it like this, but this is going to be equal to positive 5. So this is a whole number. We cannot simplify it. This is represented by a rational number, but we cannot, if we can simplify it like this, this is a whole number, it doesn't follow. And the thing about this, anytime you take a square, if you take, let's say if we're taking the square root of y squared, we notice that this is y, or this is equal to y, because y squared is, this is y squared, so y is 5, and so this also equals to y, which is right here. And when we do this, this is not equal to y. This can be, this is one thing you should always know when anytime you get into, if you have a question like this, even if it's on the SAT or anything, it's not equal to y, because the square root of a number, graphically, it looks kind of, or this is y equals root x. We're going to get into this more later, but this is the y-axis, but this is where anywhere above here, it's y is greater than 0. Anywhere below the x-axis right here, it's y is less than 0. Notice y is always going to be greater than 0. It's always greater than 0. So this value in the square root is always going to be greater than 0. So what this actually equals to is the absolute value of y. And the absolute value, all the absolute value function is, and I'll get into that later, but it takes any number within here, or within this absolute value or notation, and it changes it from the negative value to the positive. So for instance, if we take the absolute value of -5, that equals +5. The absolute value of +5 is just still equal to +5. So what we did is we took the negative and we converted it into a positive, and then the +5 stays positive. So it's always just a positive value. And that's why, when we work with this, we can't have it to equal a square, otherwise it's simplified into a natural number. And for instance, like if we have the square root of 3, we can't simplify the 3 anymore, and this equals a rational number. Because this cannot be represented as a fraction. We also have pi, which if anyone knows, it's 3.1415 ... and it continues to infinity. So a rational number, a better way to define it, a rational number equals all real numbers that cannot be simplified in fractional form. Notice I wrote fractional because this is rational numbers. And notice how we have natural numbers n. We know it's a subset of integers, which is a subset of, let's say, rational. Which is again a subset of real numbers. This is called real number. And we also know irrational number is a subset of real numbers. So, but this is excluded from this, this whole set. So, this whole set right here. Rational numbers are excluded. They're all real numbers that cannot be simplified in fractional form, which is rational number. Also, they have infinite decimal. Basically, it's where a decimal. It's a number that has a infinite decimal extension, however you word that. So if you have like 7.22 repeated, this means repeated. Infinitely many times. So this is should be better. Repeated infinitely many times. So this would be like 7.222222 ... continued. Just like 3.14 is, continued. And we can't simplify this anymore. Normally, like when you take 3.5, we know that's 3 and 1/2, or 3 and 0.5. There's only one, or it's equal to, so this is 3, which is essentially, so that's 6 over 2, right? Or 6 over 2, okay, plus 1/2. So this is a common denominator, and so 3.5, we know it's equal to 7. You just do 6 plus 1, 7 over 2. So this is a rational number, but it only has one decimal unit. So we could do like 3.25. That's this 3 and 1/4, or 3 and 0.25, or we could write this as 6 over 2 and 1/4. So we put this together essentially. So this is you're adding like these. This is included, so it's then 6 over 2 plus 1/4 But then this right here is also, we have to put this in the 4, so we multiply that by 2. So this is 12 over 4. Multiply both sides by 2, so essentially this is like 2 over 2, which is 1 times 6 over 2, which is 12 over 4 plus 1/4. And then this gives us 13 over 4. So again, it's a, how would I put it? It's a rational number, but it can be simplified. So like no matter what you break down, it consists of, a decimal that is place that is terminated. It's terminated right here. This is terminated right here. But this is not terminated. It continues. So essentially, yeah, rational numbers are anything that fits the void. So like when we have this number line, we can break this into, small pieces, but there will still be voids. No matter what we cut, there's still going to be some space, and that space consists of the rational numbers. So basically, yeah, that's all I have. It consists of, this consists of the set of all real numbers, and anytime we're constructing, once we get to the next section, we're working with 1D space. So this is like, we could define this as x-axis. Normally in algebra we define as x-axis, but it could be time axis, which is with t, denoted by time axis, or distance. Could be represented as d. So it could represent distance in feet, meters. And what we're really doing is we're taking this set of real numbers. So basically the set of real numbers exist on this number line. And we're taking the same number line and we're basically creating a new number line that we rotate, just rotate it 90 degrees, and we add another dimension. So this is an array, 1D space. So basically this is like 0. You have a point, you start with the point, and then you create a line. We have 1D, and we have 2D, which we can represent this like north, south, east, west, and any function on here. So this is 2D, and then we have, when we add another, so basically when we add another dimension, we call this 3-dimensional space. So this is a z-axis, we tend to call this is a y, tends to be the x-axis. So what we're really working in a 2-dimensional space is anywhere along, we got draw correctly, this should be a straight line. So anywhere along this plane where it's a plane such that z equals 0. So 2-dimensional space is a 3-dimensional plane, or 3D plane. It could be, we could just say it's the 3D plane, again, such that z equals, or essentially, because if we have like you have a box, so if you have a box, it's composed of many levels. Like a bookshelf, you have a bookshelf, and the 2-dimensional plane is just, we're representing just levels, 0, for instance, and we're just projecting that, like this is just a square. Or it goes on to an infinity. We can make it a infinitely large plane, but it's just a plane, and that's what we work on. We're just working on a plane that's just not extended in the z direction. And then of course if we want to add like a time axis, you got 4 and you continue. But yeah, this is all I had today. I hope it helped, and I will continue to the next session and start working in 1D space, and then moving on and how to solve problems in 1D space, and then moving on to two-dimensional space and formulation of the coordinate grid, which I think is very important in algebra before proceeding to more difficult concepts, because everything is going to build up in layers, and just like this bookshelf or just like this coordinate grid, it's always going to build up in layers. And if you have the fundamental knowledge, you can utilize this in any field. Very important. Um, and it's algebra's definitely utilized in many different fields. And I think it's a critical subject to learn. As with geometry and calculus similarly. But yeah, I'm just gonna stop right here, and hope you enjoyed.